All right, so the next presentation is going to be given by three people, so I'm not going to dive into all the biographies here, so if you can all just give a welcome to Eric Dull from Cray, Rachel Kartch from the CERT, and Bob Techentin from the Mayo Clinic. All right.
Hi, everybody. I'm Rachel Kartch. I just wanted to explain really quickly how this talk is going to work. There are three of us. Eric Dull from Cray is going to be speaking first. He's going to be giving you some background information about the project we've been working on together. Next, I will be speaking about some of the key decisions that were made during this project. And then finally, Bob Techentin from the Mayo Clinic is going to be, there he is, hey Bob. He's going to be speaking about sort of some real-life implementation and examples of the kinds of work we've been doing. I don't have a punchline for that joke on there. It was my first choice for the title of our presentation, but for reasons I don't understand, it wasn't accepted. I just want to mention, because there are three of us, although it does look like we have a little bit of extra time, please hold any questions you have for any individual speaker to the end after we've all spoken. That's in part because it's possible that one of the later speakers will actually answer your question. And it's also just to make sure that each of us has enough time to speak, because I don't want me and Eric hogging all the time and then Bob doesn't get to talk. That's it.
Yeah, Bob did the actual doing here. We just did a bunch of the motivating, so he's got the cool stuff and the visuals. I don't have a punchline for the joke either. For my portion of the talk, I'm going to cover why do we care about graphs. I'm very heartened about the talk we just saw because it helps motivate that. Why do we care about RDF, or why did we think RDF was an appropriate thing to use, and why did we decide that we wanted to stand up the Open Cyber Ontology group? I talk about graphs a lot, and that's why there's the first bullet on there. A graph is not built in Excel. It's a fundamental data structure in computer science. It consists of nodes and edges. We saw one example where we saw IP to IP relationships. We saw another example in the talk previously where we saw AS to IP relationships. It doesn't really matter. We like graph, we being me here as a graph analyst, like graph because they do some handy things for us, but we just need to all understand that this is what graph means. Now, the reason we really like graphs is that it's a native representation of a lot of transactional structured data, particularly in computer networks. Who knows what BGP means? Okay, somebody's awake. Can anybody draw it where you have AS1 is to AS2 as AS3? This is a graph, right? We can reason about these without a piece of paper on the frost on the side of your beer mug. This is the native representation for the data, which makes understanding and thinking about the way you want to analyze it in a graph a very easy thing to do. Dr. Collins is the person I'd like to cite for my second bullet. We have a lot of available graph algorithms, and we have a lot of ways they can be applied to computer network analysis problems. One that I'm particularly fond of is Jeff Janey's work from 2011, using betweenness centrality. Does anybody remember seeing that talk? Hey, cool, excellent. A few of us are still awake. It was a really nice talk that showed how you apply betweenness centrality to find beaconing botnets in the middle of the night. Additionally, the social network analysis gives us a lot of algorithms that we can use. I'll talk about some of these later this afternoon. We like graphs because you get the data merges for free. We've all had to try to slam multiple types of data together in a SQL-like database, and it really, really is painful, and its performance is really bad. By putting it into a graph, as long as we know what the edges mean, we get that merge for free, modulo those couple that little computer science detail there. And there are engines available that let you do graph from a napkin to a trillion things at varying sizes and scales of availability. So this makes it very easy to get started doing this sort of stuff. I mentioned it's a native representation. Follow the flow is actually a really big deal. You can think of this as activity attribution, or kind of following the logical step as things move through a network. It's something that we all do natively using grep and awk and Python. So we think that putting in a new graph engine means you can do it faster. Sparkle is SQL for graphs. Has anybody heard of Sparkle? Yes, excellent. This means that you can use kind of a bunch of that same SQL thinking to query graphs, and most of the graph engines that are out there do Sparkle, at least the ones we play with. And this last point is one that I think everybody in the audience can get behind. I'm really lazy. I don't like having to hold people's hands to do analysis, and so everything we can do to get away from an interpreted language or a compiled language into a query language that people don't think is programming makes it easier for people to do analysis, makes it easier for us to hand analytic concepts out to people, and makes it more likely that they will be able to perform without a subject matter expert sitting next to them. We really like RDF because, and we being the OCOG here, because it's flexible. Any structured data can be represented in RDF. Question mark S, question mark P, question mark O is RDF, is Sparkle speak for any subject, any predicate, any object. A question mark is where you have a variable. So a Sparkle engine would take that query and basically do a table dump for you. RDF is the triple form. So in order to put a element from a traditional relational database, you'd have a primary key as a subject, you'd have a predicate that describes the relationship from the primary key. This is probably the column header, and this is the contents in that row. This makes it really easy to map complex tables that we're used to thinking about into this relatively simple structure. Schemaless means that you don't have to predefine everything. I've worked on some really big graph engines and some really big graph projects. They're really a pain in the butt because you have to go through the change control board. It takes about 6 months every time you want to add a new entity. And I think we can all agree that computer network analysis is something that operates faster than 6 months. You see new feeds, new data types stand up on a pretty regular basis. And RDF gives us the flexibility with the little o ontology and the schemaless nature where RDF defines itself. And as long as you know the way the data is being represented in terms of what the subjects mean, the objects mean, and the way the predicates are spelled, you can write queries across it without having to do any pre-compilation steps. It's really powerful, and it means that we can put new data into an existing database or an existing RDF structure in terms of seconds. So this confidence scoring that we were just talking about, we can actually insert in which analyst looks at which alert on which date time and just roll that into the database and now have this living, breathing thing, which is all of your information about the way your organization has done that analysis. Ontologies is a magic word that is going to get a lot of people throwing donuts at each other. There's big O ontologies, little O ontologies, there's taxonomies, and there's schemas. What we really mean here is an ontology is a definition of things, their relationships to each other, usually in terms of a hierarchy, and their relationships to other things, all within the space. We're attempting to describe a small practical portion and not boil the ocean. Now the reason we're doing this is for two things. One, it allows me to say things that use semantic reasoning concepts, called forward inferencing inside of Sparkle, but it also allows me to standardize the way the data is represented, which is the thing that OCOG was really driving at, so that we can provide a common way across different organizations of representing NetFlow data semantically, so that we can get done writing parsers and start writing more analytics. Which is how we got to this slide. My colleague, who unfortunately just left us recently, Steve Reinhardt, and I did a number of engagements with a number of people who actually wanted to do analysis. After about the 5th one, we got tired of trying to have to explain to people what network data should look like in RDF. And so we called up our buddies at Mayo, at SCI, PSC, and a few other folks. We got together in June, and we worked for about 6-8 months on agreeing on a way to represent NetFlow and RDF. And so now Rachel can speak about kind of some of those key decisions we made during that 6-month process.
Word to the wise, if you are going to be up here speaking, wear something that has a waistband so that you don't have these boxes clipped all over your footwear. So let's start with an awkward moment. The awkward moment saved only slightly by the fact that there's a lot of clip art available online where I can put a coming soon stamp on the slide that was supposed to show you the URL where you can see the ontology now. Unfortunately, you cannot. It is not available online yet. It's still going through the release review process. I know that some of you are very familiar with that. We are hoping that the ontology document will be available within the next several weeks. So, you might want to bookmark that URL and click, obsessively click it repeatedly until the ontology is available, because we really are interested in your feedback on what we've done so far. There may, in fact, be something available at that page now based on what my colleague may or may not have done this morning. But that doesn't actually matter, because it was not my plan today to go line by line through the ontology and explain it all to you. That would be absolutely horrible for everybody involved. Instead, I just wanted to talk to you about the big picture and explain to you what we were trying to do and why we made some of the decisions that we made. So we have a dream. This is our dream. There may be a quiz on this diagram later. I'll just let you know you may have to fill in all of those boxes from memory. The idea is that we wanted to develop sort of an ecosystem. So the Open Cyber Ontology should incorporate lots of different data types. These boxes here are really just an example of some of the kinds of data that we could put in there. It's certainly not intended to be an exhaustive list, but I wanted to have this diagram here to make it clear, because I'm going to be talking about IPfix, that we didn't start with IPfix because we think IPfix is the only thing that should be in there. It's, as you'll see when I talk a little more, it's because we had to start somewhere. But this is the dream, keep it in mind. So key decision number one was, where do we start? So the group first got together in Pittsburgh in June, and we talked a lot about two different types of data. We talked about transactional data and we talked about enrichment data. Now the goal, the dream, that big picture you saw on the previous slide, we want to have all of it in there. We want to have a really rich representation of network objects and network events, and we want to be able to do some serious analysis. But we have to start somewhere. So where do we start? Well, transactional data doesn't give us all the cool context stuff. Transactional data, what I mean by that is things like DNS, DHCP, Active Directory, network flow, routing updates, pretty much things that represent transactions, things that represent things that happen that you can see in your logs, that you can see on the wire. Enrichment data is different. Enrichment data talks about things like who owns a particular asset, who owns that net block, who's the sysadmin for that particular organization, is that an internal or an external machine, is that a user machine, or is that a web server, or is that a mail server. All of that kind of information that can really help you do analysis beyond just, this IP talk to that IP on that port. The problem there is that enrichment data is not as regular and predictable as transactional data is. So transactional data, for the most part, it's already defined. We've already got standards. We already know the formats. So it's relatively easy to take transactional data and figure out how to represent it in RDF. We'd be doing a little bit more of a heavy lift with the enrichment data. So we made the decision that we were going to start with transactional data, and it made sense to start with network flow, because that is a type of data that a lot of people use for operational analysis and security analysis. So key decision number two, what flow standard are we going to use? I'd just like to see a show of hands here. How many people in this room have very strong, passionate opinions about which network flow standard is best? Bless your hearts. I am not going to get into that religious debate. I would be absolutely happy to have that conversation tonight. What time are they starting to serve the drinks tonight? Does anybody know? 6:45 tonight. I would be happy to have that argument with anybody who wants to have it. For now, I'll just suffice it to say that we decided to go with IPfix for a couple of reasons. Reason number one is because it is an open standard. We thought it would be best to stay away from something that was, vendor proprietary. The second reason is because IPfix is more or less backwards compatible with NetFlow version 9, since any field that's in NetFlow version 9 has its equivalent in IPfix. It was kind of a two birds, one stone sort of situation. So we decided to start with IPfix, but again, think back to that picture I showed you. That doesn't mean we're ending with IPfix. It just means it seemed like a really good place to start. So key decision number 3 is, how do we identify a flow? The challenge here is, so in one of the slides that Eric had, you saw that an RDF triple is a subject predicate object. Well, for most of the triples that we would be creating with this ontology, the subject is going to be the UID for the flow itself. It's going to be the flow has this source address, or the flow has this byte count. So how do we represent the flow? The tension here is it would be really nice to have something that's very short and very human readable for our flow UIDs. The reality is, if you want to keep that space collision free, or as close to collision free as possible, you can't have nice little identifiers like flow 1, flow 2, flow 5 million. The decision we made is that the UID is going to be a 128-bit MD5 hash of the 5-tuple for the flow plus the start time. For those who aren't familiar, the 5-tuple is the source IP address, the destination IP address, the source port, the destination port, and the protocol. So we put those together, we add the start time, we do the hash, and then we base64 encode the resulting hash into an RDF compatible string. You can see at the bottom there's an example of what that looks like. I should probably have put like gigantic quotes around readability, because obviously that's not a string that anybody's really going to be able to remember, or quickly be able to say, oh yeah, I remember which flow that was. It was MJA0, blah, 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 blah. But it seemed like the best compromise, because we really needed to make sure that we could have unique flow UIDs. Also, somebody in our group did do the math, or find a citation to the math about the likelihood of a collision using this method. Yes, it is possible. The likelihood is so incredibly low that none of us wanted to think about it anymore after that. So we went with this method, but if anybody has a better idea, we are open to it. So key decision number 4 is, which fields are core? I'd like to see a show of hands again. Has anybody in here ever done standards work? A few people. So it's super, super boring. It's like the worst. And so if you have an argument that lasts for more than 2 consecutive meetings, that counts as exciting. So this was, I want you to understand, looking at this slide, this is the most exciting thing we got. We had some pretty significant and lengthy debates about which fields should be in the core of the standard. The two sides of the argument, on the one hand, there were people who really wanted to keep it minimal, to say, we don't want to require people to have 12 or 14 fields present whenever they convert their data to RDF. It could create storage problems. We can't assume that everybody has unlimited storage. It creates verbosity problems. On the other hand, if we set the bar too low and we made it too easy for people to grab 3 fields and they're done, those people are really going to be limited in their analysis, and they're going to be limited in their ability to use the standard, and in the end kind of might be shooting their own foot by trying to do too little. Also, because one of the goals is information sharing, so the idea is that I have a bunch of flow data and I convert it, and maybe I want to share that with Eric, and he's got some flow data from a similar incident or a similar time, and he converts his. And if we're all over the map with what fields we have, it could make that collaboration a little more difficult. So the decision we finally came to is, we came up with a compromise, and I'm going to show you on the next slide what this looks like. We developed a series of field classes at different levels. So level 1, flow identity, this is your core. This is your minimal number of fields that have to be present if you're converting your flow data into RDF. It's the 5-tuple plus the start time. Level 2A is flow quantity. That's level 1 plus your packet count, your byte count, and your duration. Level 2B is protocol specific. So this only applies if your flow is TCP or ICMP, and it'll include level 1 plus the TCP flags and the ICMP type code. Level 2 is flow detail, which includes level 1 plus all of level 2A and level 2B. Level 3 is the standard. This is when you see the ontology document, you'll see that this is the level that we recommend people use when they're using the ontology. We recommend that they stick with level 3, which is all of level 2, plus exporter collector information, conversion date information, what file you got your flow data from, and the version of the ontology that you use to do the conversion. Levels 4 through 99, it was noted on a previous slide, there are over 400 information elements in IPfix, so we decided not to go ahead and put all the rest of them into levels, but there's certainly more work to be done, and if anybody wants to volunteer to help us with this effort, we would be happy to talk to you. So that's what I got. Bob is going to come up now and talk about some stuff that they've been doing at the Mayo Clinic.
Thank you, Rachel. Okay, cool. And I know I'm the only thing standing between you and break, so let's get on with it, right? So I've been working in a research group at the Mayo Clinic for probably a little while now, and I'd like to emphasize at the beginning that this is really a collaborative effort, not only between Mayo and CERT and Cray and PSC, but also within the Mayo Clinic. And this, you know, the notion of collaboration dates back to when Doctors Will and Charlie founded the group practice over 150 years ago. We know we need to work together, especially when we have folks who have a lot more expertise in different areas, and we can exploit that teamwork to really get a lot of good stuff done. And I can also get other people to do work for me, and that's important. But I just wanted to mention that you know, I work in the Special Purpose Processor Development Group with Dr. Barry Gilbert. David Holmes is also here. He runs the Biomedical Imaging Resource, another key resource at the clinic. And of course, we've been collaborating with the Office of Information Security, run by Jim Nelms now. And so internally and externally, we're doing a lot of collaboration to understand what some of these graph techniques are in the models and build data sets and use those. So in the last 150 years, they didn't actually start with a lot of networking, but we're getting there. And I just wanted to say that it's a non-trivial enterprise. We're not looking at just a little lab in a corner somewhere. The network is large enough to be interesting and provide challenging problems. It spans many states. We've got tens of thousands of employees and millions of visitors. We've got the stuff you'd expect to see in a Fortune 500 kind of company with lots of proprietary software, commercial software. We've got actually several different medical schools, so you've got students, and they're always known to be ill-behaved. You've got researchers like me who'll download and run almost anything. So there's all kinds of stuff going on the network, right? It's big enough to be interesting. We're collecting right now on the order of billions, well, more than billions of flows a day to try to do some analysis. So it is kind of challenging how we do that. As we look for how we can do some of the analysis, the OIS folks, the Office of Information Security, purchases tools. They're putting in the best of breed tools there. They've got some real good experts. They've got the response center and the like. They're doing all the right things from that perspective, but we're also trying to look forward to what are we going to be doing in the future and how do we address some of these things? Well, one potential way we can do some analysis that the tools that we're putting in place, the commercial tools and the other things, is using some graph analytics. We started looking at this as an alternative quite some time ago, really to try and understand how we can find the needle in a haystack, or the nuggets that are inside of our clinical medical records. We know there are things hidden in there that if we could only find them, it would be tremendously valuable. The example I'll cite is FenFen. If you want to look up the Wikipedia page, you can read the whole story. But FenFen was a prescription diet drug in the 90s, very successfully helped a lot of people lose weight. And it was just happenstance, it was careful and deliberate that a Mayo Clinic analyst noticed in a couple of dozen cases over a period of several years that there were some heart patients that had been taking FenFen. They weren't able, from the Mayo Clinic records and a few dozen instances, to prove causality, but there was definitely some correlation there. They published a paper, and it was very soon after that, the medical community got together and proved that, in fact, FenFen does cause heart valve damage and is a dangerous drug, and they pulled it off the market right away. That kind of stuff is hidden in the medical records, sometimes over a span of years, and we need to be able to find it in a methodical way, even if we don't know what we're looking for. And this graph analytics might be a way to do some of that. So in 2005 was the first time we started looking at this Cray XMT supercomputer. Our research group does high-speed electronics and supercomputer stuff, and we just met people and they said, you should look at this. Well, here's a different kind of machine. It does this kind of analytics differently, and even though we've got some of the best technology you can get for building the gigantic data warehouse and the data mining for our clinical medical records, this thing can do something different and we should take a look at it. And so we've done that. We've got a little baby supercomputer at Mayo now named Grace, and we're using graph analytics on some of the clinical data. Our friends at Cray said a while back, oh, by the way, this might work on cyber too, so let's take a look. We contacted Office of Information Security and set up a little project where we'd try some of this stuff out, and that kind of led us down this road into looking at NetFlow. But it's not just NetFlow, it's all the other stuff too. So this is my cartoon of all the kinds of information we'd like to capture together in a semantic model, where everything has the meaning and relationships through these edges in the graph, right? Some things are definitely need to be in there. The transactional data, of which flow is the biggest one, right? The other static data about the configurations of our networks and how we've built the thing, information about the assets that are on there, the software they run, the users and all that. We've got all that information. Can we bring it together in a graph model? Doctor Who is clearly outside of the bubble, so we don't want to put him into the graph model, but we're thinking about that a little bit, okay? So we started working on what we ended up calling the Mayo Clinic cyber model, because we had to have, a cool acronym, which was basically just a way to spell all of the elements in RDF so that we could connect the graph model together. And like Eric mentioned, we did this a couple of times and realized we were kind of repeating the wheel invention there a couple of times. So we talked about how can we do this once and then just for the basic stuff, and really the standard syslogs, things like flow data and other information should be pretty standardizable. We can get that done once, and then we can focus on bolting on all these other important things from the enterprise information that will allow us to do a more sophisticated model. So this is a picture of the MCCM that we've used to try to describe it a couple of times, and on the left is a NetFlow record depicted as a graph. So your NetFlow identity that Rachel described is kind of like the vertex in the middle, and it has edges connecting it to various attributes. And so it has things like a duration and number of packets and things like that. So every flow is identified that way. The spider itself doesn't look too interesting, but it does get interesting when you pile a whole bunch of flow data together, because suddenly you have connections between things on ports and protocols, and you can ask questions about how things are related in different ways, and that's pretty interesting. That's kind of where the OCOG is right now, where we've said this is a standard thing, let's do that. The model we're working on is more on the right, where we're trying to bring together other stuff to go with not just the flow data and not just the log data, but what do we know about our systems? Can we have relationships that we understand between the MAC addresses and the IP addresses, the organization that bought the machine, the software it's supposed to be running? We'd like to integrate all these data sources together in the semantic model, and it's pretty straightforward if you can capture the data, translate it into these pretty simple RDF triples and bring the model together. So that's just kind of a view of where we're going with it. The nice thing is that once we put all this strange stuff into a graph, we can use some different math on it. And in the graph, everything is just vertices and edges, and you can apply some techniques. Eric mentioned betweenness centrality. Here's a little different one. It's a Jacquard similarity score. It's really set theory. We're just looking at the common neighbors of A and B. And you can do a little math and come up with a number that says this is how similar these two vertices are. And pretty powerful. In the simple case, you can just build a simple map of which IP addresses talk to which other IP addresses and compute similarity across the entire spectrum of all the systems there. So you end up with essentially a really big matrix with, third of a million IP addresses on each access, and you can put a number in every location there for how similar are these two IP addresses based on their behavior. You could look at just the fact that they talk to each other. You could look at the protocols. You could look at the traffic quantities or other information. But you can do this kind of similarity computation pretty easily. And we don't necessarily need to know what we're looking for when we apply this kind of an algorithm. In fact, sometimes we might not even really know for sure which dimension we're looking at. Are we looking specifically at IP addresses, or are we looking at similarity of users, for example? And we can kind of explore the graph algorithmically, regardless of the specific kind of data in there. So once you get all these similarity scores out, you can plug them into something else. In this case, it was R, to do a little hierarchical clustering and then give us a heat map displaying the similarity values. And we can then look at this and try and decide what it means a little bit. So this particular one was just some of the noisiest systems on the Mayo network, and we clustered them and looked at them. And sure enough, the groups on here do have some meaning. And it's not always just, oh, well, this is DNS services. Obviously, those are obvious. We did the same thing at our department level and took a list of IP addresses to our sysadmin and said, well, are these actual similar systems? And yeah, those are the printers, and these are the oscilloscopes in the lab. So the methodology does seem to help us find things that are interesting, even without having a specific question. So similarity is good. Dissimilarity is also good. That's kind of the converse when you want to find the unusual things. So we're looking forward at how we can use some of these algorithms to explore some of these spaces. So I'd like to just then conclude for all three of us. We're trying some graph analytics stuff. Actually, I think Eric is going to give a talk later today and tell you how amazing it really is in a practical sense. But we've been doing some at Mayo also, and having one of these standard ontologies just to spell things the same way so we can all work together seems to be a significant benefit. So we're looking first at the flow, and we'll look at some of the other transactional data sources, and we'll see how we can make that so that we can bolt on our enterprise-specific stuff that's going to make the analysis work well. So we've already been doing some of the real-world analysis. Some other folks have too. And I think this is going to help us move forward. I'm pretty excited about that. But actually, I have an obligatory butter up the audience too, because I'm pretty excited that we're really presenting this standard and announcing it here first in this community, because I can't think of a better place, now that I've met a bunch of you, that would give us an opportunity to discuss what the standard is and how it could work in the future. So thanks for your attention. If my colleagues would like to be available for questions, oh, there you are. Are there any questions? I took all your wiring, so
one
you're going to have to
question.
use that.
One question. It looks like you've got running code, which one old standards organization used to use as sort of a benchmark. In what other sense is this going to be a standard?
So I'm going to be optimistic for a second. We're going to put it on the website. We're going to ask you throw rocks at it. And then it's, Bob's group is writing demonstrator reference converter code, and then the theory is you can all go use it. You being whoever wants to do RDF analysis for cyber, and we can actually go check in Sparkle that are example algorithms that accomplish things.
So it would be a standard in the sense of an open source project that works and people adopt it.
Yeah, so I'm going to look at David right in front of you, who has done actual standards work, and say,
I have two, and I ran the other way.
Yeah.
Jim.
When you did your Kartch similarity clustering, were you just looking at IP-to-IP data, or were you looking at across object types?
So that example was just IP-to-IP data. It was an interesting challenge computationally to do, I forget, how many billions of similarity scores did we have when we were looking at 300K, just internal IP addresses. And doing similarity against comparison of all of those took a little bit of time. But the same thing applies to the more complex models. And as Eric hinted, when you build the graph model, right, you can match across any kind of dimensions you like. It could be the quantity of traffic, or you could do another hop over into the system asset database and look at the version of operating system they're running on. So you could do that kind of similarity scoring almost anyway. That one was just IP address to IP address.
Okay, thanks.
So I look at the data sets that you guys are attempting to collect, and there's a pretty big disparity. And starting with transactional sources is, to some extent, we have a lot more structure on how to consume those. But as you, and you even kind of allude to it on the slide, as you take in things that are more static and structural sources, you're introducing a difference in temporal components of your data, right? So the transactional sources are exactly what they say. They have a relative lifetime. They show you a snapshot of information of what they observe at a point in time, and then you have a set of data that it has a completely different lifetime. And so as you bring that into one graph, have you considered how to deal with those
Do you mind if I take
facts? And
So that's a great question, and we have considered it, or at least this portion of we. Most of it is by putting start and end times, or at least a start time of this is when I ingested these facts into the database, or this is when they were apparent. We can use filtering inside of Sparkle to actually say, let's look at this time slice, let's look at this section of the traffic, and then which enrichment data is applicable over that time period.
So, I'm going to guess that you're not far enough along to see what the impact or
In terms of performance, no, we have no numbers, right? But
It's not necessarily performance, right? I mean, so IT allocates an IP address or a subnet or whatever, right? And that's a manual, human-involved process, and it has a relatively long-lasting impact compared to a TCP connection, right? Whereas, Mayo Clinic goes and asks Aaron for an ASN allocation, and it has a much, much longer, impact and relevance compared to the subnet allocation, right? And so these things should be accounted for in the weightings or kind of the overall impact of what they mean in the graph.
Right, and so, I guess I'll say, yeah, and we're not that far along yet. I mean, that problem exists today. That
That's
problem
fine.
exists with any kind of analysis you're doing. When I'm sitting there messing with BGP, I need to make sure, okay, if I'm looking at data from October 12th, I need to make sure that the country code data that I have also, kind of put in there so that I know what country code goes with which AS, I need to make sure that that country code data was from about the same time frame. So, so that problem exists whenever you're dealing with multiple data sources being brought in from different places, and certainly it's something we're going to have to look at. Right now, we're still in the let's talk about that kind of phase, so I don't have an answer for you.
Okay.
yes, sir.
I was somewhat puzzled by your discussion of hash collisions, because the real issue is what happens when the 5-tuple plus timestamp collide. If we have data that are coming from multiple small private network addresses, I would say that there's a very high probability, unless your timestamp is gigaseconds or something like that resolution, that you will have multiple addresses and protocol port collisions with the same timestamp at a fairly high probability. Consider protocol 17, port 53 source, port 53 destination as a very common flow. Now, all the degrees of freedom we have are the IP addresses, and if we assign by a convention the DNS server locally to a single small address within the subnet block, it's going to be very high that we'll have collisions across blocks. So if I have a flow from my network and you have a flow from your network, there's a non-zero probability that we're going to have the same unique ID, because the same 5-tuple is going to hash to the same unique.
So this brings up a great point. We're intending this for an organization to use, right? When you start talking about this cross-network behavior, something in level 3 that we haven't shown you because it's still being baked. Involves the collector as part of the overall network. We need to look at rolling the collector specificity into the UID, which will remove that collision for you.
Not necessarily, unless you factor the port on the collector in there. If you have multiple private networks feeding into the same port, we're hitting this. This is why I'm bringing it up.
These are great.
Yeah.
These are great problems.
And this is exactly why we wanted to present this here and put it on the web, is because we want this kind of feedback. I'm going to admit, I personally felt that the likelihood of a collision of the 5-tuple plus the start time was relatively low. It's certainly not zero, but I felt it was relatively low. But also, I'm not a mathematician, so happy to get that feedback.
Yeah, in a couple of iterations through our mucking around with the Mayo model, we used a couple of different inadequate hashing approaches. And we did in fact introduce collisions in our own data, and you can find them pretty easily in the graph. So our notion, I think, here was to let's build something that looks like it'll be okay. We put in some description of the collector with the notion that we'd be able to bring in separate data sources into the same graph and be able to rationalize those, but we don't have a lot of experience doing that yet. As we go along, we may find that we have to do things differently, or we may find that it never occurs in practice. I don't know. It may very well be likely.
So any conversation that involves standards eventually comes around to the joke that the wonderful thing about standards is there being so many to choose from. And I was just curious whether you'd looked at STIX and OpenIOC and the various other multiple competing pseudo-standards for more threat-specific information and how you might interrelate with those.
We're a little aware of those. We haven't been squinting at them heavily. My expectation would be that as long as the entities are represented the same and it's representable in RDF, we're happy to take any other work anybody else has done.
All right, we're in the demo room.